Alright, so section 10-1 is on polygons, which we've already discussed several types of polygons, triangles, quadrilaterals. But we're going to look at the definition of a polygon again. You should know what that is. A polygon is a closed figure formed by straight segments. So if I gave you a figure that looked like this, would that be a polygon? No. I'm missing one of my pens. How do things just disappear up here? Aha. Alright, so this is not a polygon. Then we're going to break a polygon into whether it's convex or concave. And it's easier to envision what a concave polygon looks like, because what does a cave look like? It's pushed into a mountain, isn't it, typically? So it's hollowed out of something. So if something's caved in, like if the ceiling were caved in, it would be coming in towards the interior of this room, wouldn't it? Yeah, kind of like a hole. Something's pushed in a dent, right? So we're going to go ahead and draw a concave first. So here's one side. Here's another. Another side. Another side. And then our final side. So it still is a polygon because it's straight. Got straight lines and it's a closed figure, so it's still considered a polygon, but this is concave specifically because of this right here. Whereas if you drew a very similar polygon, but it was not caved in, so to speak, it would look like this. So the only difference between these two polygons is this vertex right here has been pushed in to the interior. How do you know that's actually pushed in? So here's your technical definition. Ready? And then I'll show you how it actually looks with a ruler. So a convex polygon occurs when the sides of the polygon are extended to form a line and that line contains no points in the interior of the polygon. So, how does that look? It occurs when the sides of the polygon are extended to form a line, and that line contains no points in the interior of the polygon. So if I take the convex polygon and I use a ruler to extend any of the sides, so we'll just take, I'm going to go ahead and take this side because you'll see why in a minute. So I'm going to extend this side. Do any of the points of that extension lie in the interior of the polygon? No. And I could do that for any of the sides. So if I extend this side, it wouldn't go through the center. If I extend this side, it doesn't go through the center. Or this side, or this side. So none of the 6 sides on this figure extend and go into the center. But if I go to my concave polygon, this side doesn't extend and go into the center. This doesn't, this doesn't, this doesn't, but the minute I go to this caved in part, look at this side. So if I extend this side, isn't that part right there in the interior of the polygon? So it doesn't necessarily have to happen to all sides, and the other side that's caved in with it, this side does the same thing, doesn't it? This part right there is in the interior of that polygon. So you're either visually looking for a vertex to be indented into the interior, like somebody's pushed in on it, whereas this one you can envision some person standing in here holding and pushing out those sides, right? He's standing inside and pushing out all the vertices and all the sides of that polygon. Whereas in here he got squished, didn't he? Okay. All right, so then you need to know what the names of the sides of these polygons are. And all of these you have to know that we're going to write down. So what's the fewest number of sides that it takes to make a polygon? 3. You cannot make a polygon with 2 sides, right? So here's 2 sides. First of all, it's not closed, right? There's no way to close this unless I touch the 2 sides together. If I touch the 2 sides together, they just become a line, don't they? So I do have to have a minimum of 3 sides. What's that thing called?
Triangle.
Triangle. So you should already know that one, right? Now, I don't want you to call it, in this particular chapter, I want you to use generalities. So if you have an isosceles triangle, just call it a triangle. I'm not necessarily looking for specific names. So then, what's a 4-sided figure called? Nope. Quadrilateral. Because a rectangle is a special quadrilateral, a square is a special quadrilateral, a rhombus is a special quadrilateral. So unlike the quadrilateral chapter, if you call a square in this chapter and I'm looking for the polygon name, I will mark you off. So do be careful because I want to know, do you know that it's called a quadrilateral? All right, then we come to 5 sides. What's that called? Pentagon. Do you know why the pentagon in Washington, D.C. is called the pentagon? Because it has 5 sides. And then a 6-sided figure, hexagon. Did you know that honeycombs are made of hexagons? They are. 7 sides. What's a 7-sided? Heptagon. Is there any other name for a 7-sided figure other than heptagon? I heard it. Go ahead and say it. Somebody's whispering. It is septagon. You need to know both of them. The reason why I say that is either one's acceptable to me, but if you're taking the Ames test and the Ames test calls a 7-sided figure a septagon and you've only learned heptagon, are you going to recognize what they're talking about? No. So you do need to know both. All right, so then 8 sides should be easy. Octagon, what's the perfect outside form of an octagon? A stop sign. Perfect. 9 sides. And it is spelled N-O-N-A-G-O-N. Nonagon, nonagon, either way is correct. Then 10 sides. Decagon. Oops, don't know why I spelled that with an A. So decagon. And then we're going to skip 11 and we're going to go directly to 12 sides, my favorite polygon name. Anybody know?
It's really long.
It's a great name. It sounds like an extinct bird. All right, here we go. Nope. Almost. Dodecagon. You know the dodo bird? Dodecagon. It is long. It's a great name though. Dodecagon. And then after that, these are the only ones I'm going to require you to know. Anything other than these will have n sides, right? You're going to call it an n-gon. So let's say it has 15 sides. You're going to call it a 15-gon. There is actual real names for them, but I'm not going to require you to know them, so you can just call it an 11-gon or a 15-gon or a 20-gon. Okay? Now your textbook might call a 6-sided figure a 6-gon because they want you to name it. You're not allowed to name it that. All right, so flip it. Then we're going to talk about regular polygons. Again, you should know the definition of a regular polygon because we talked about that in an earlier chapter briefly. Anybody remember? There's two things a regular polygon has. What's one thing? Equal sides and equal angles. So a regular polygon is a special polygon with all sides congruent and all angles congruent. So your sides are congruent and your angles are congruent. There are two different types of angles in a polygon. There are interior angles and there are exterior angles. This implies that all interior angles are congruent and all exterior angles are congruent for that regular polygon. Then I've drawn for you several different types of polygons here. They're not necessarily regular polygons, they're just polygons. We're going to talk about diagonals. So look at the quadrilateral. I want you to take that vertex right there, and that vertex only, not all of the vertices, but just the one vertex. And I want you to draw as many diagonals from that vertex as you can. Now a diagonal has to go from vertex to vertex, and it may not be the side of a polygon. So how many diagonals can you draw? Just one. So I can only draw a diagonal from that point to that point. So I can draw one diagonal only. Notice what's created when I draw a diagonal. What do I create inside the polygon? Triangles. So go down to this table here. A quadrilateral has four sides, and we created two triangles with one diagonal. Then go to the pentagon. I'm going to choose that vertex. We'll talk about why we skip triangle in a minute. You'll see why. How many diagonals can you draw from that vertex? Two. I can draw one from here to here and from here to here. So I do get two diagonals. How many triangles were created? Three. So a pentagon has five sides, three triangles, two diagonals. Hexagon. I'm going to choose that vertex. How many diagonals? Here's one. Here's two. And here's three. Right? Three diagonals. Hexagon is six sides. And how many triangles were created? Four. So you should start to see a pattern as the number of sides increase by one. What's happening to the number of triangles? Increasing by one. What is the correlation between the number of sides and the number of diagonals? Four sides, one. Five sides, two. Six sides, three. What's always happening? Four, one. Five, two. Six, three. Four minus one, three. Five minus two, three. Six minus three, 3. So the number of sides is always different by 3 for the diagonals. So if I had a 100-sided figure, how many diagonals could I draw from one vertex? 97, because what's 100 minus 3? 97 is a lot of diagonals. Nobody should have earphones in. I see one. Did you remove yours? You can't be listening to that and me at the same time. He goes, yes, I can. I'm multitasking. All right, so you should now anticipate how many diagonals the heptagon is going to give you. How many do you anticipate? 4. So from here, let's see if we can draw only 4. So here's 1, 2, 3, and 4. So I have 7 sides. And here I should anticipate that I have 5 triangles. Did I get 5 triangles? And isn't it always one more triangle than the diagonals? There's a lot of patterns that are going on here. And then your octagon, we anticipate 5 diagonals. 8 sides, I anticipate to get 6 triangles. So let's see. 1, 2, 3, 4, 5. So I did indeed get 1, 2, 3, 4, 5, 6. All right, so Jake made a comment, we skipped the triangle. Why did I skip the triangle? How many diagonals can you make from one vertex of the triangle? 0. If you look at the pattern, you go backwards because quad is 4, so backwards would be 3 sides. We should make 0 diagonals, and that's true. You cannot make a diagonal from a vertex in a triangle. It's impossible. And so the triangle has 3 sides. What's the number of triangles in a triangle? 1. So let's go and try to find the sum of my angle measurements. Now we have down here at the bottom an n-gon, right? So that means that the number of sides of an n-gon is n, right? Now let's try to figure out the number of triangles. So from 3 to 1, 4 to 2, 5 to 3, 6 to 4, 7 to 5, 8 to 6. It's always minus 2, right? So you're right, isn't this n minus 2? So if I had a 100-sided figure, how many triangles would I make inside? 98. And it's important because if you don't know the formula for the sum of the interior angles of a polygon, you can derive it by thinking of the triangles that are created by the diagonals. And so the sum of the angle measurements of a triangle, the interior angles add up to what? 180 degrees. What about a quadrilateral? Would you learn? 360. And so let me just point out that you've got 2 triangles. What's 2 times 180? It's also 360, right? So we could either add, because we have an additional triangle here, we could add 180 to here, or I could be thinking, I'm sorry, for 3. I could add 180 to here, or I could be thinking 3 triangles times 180 degrees is what? $540 degrees. Then we can do 4 times 180. What? 720. And then 5 times 180. 900. 6 times 180. 1,080 degrees. So what am I going to do for... So we've always been taking this column and multiplying it by 180, right? So we're going to take this and multiply it by 180. Now, if I were you, I would put 180 first times n minus 2. Didn't we just derive the formula? Take the number of sides, subtract 2 from it, and take that and multiply it to 180. And that's why the formula is what it is. So then let's look at our 2 theorems here. You've got your interior angle theorem. So our interior angle sum theorem, which we just derived, says if a convex, and it must be a convex polygon, has n sides, and this is S, not a phi, this is S, and S is the sum of the measures of its interior angles, then here's your formula. S is equal to 180 times n minus 2. All right, so then we're going to go to our exterior angle sum theorem. This trips you up all the time, but it's so much simpler than the interior sum theorem. So imagine any of these polygons inscribed inside of a circle where all the vertices touch the circle. What do all the angles in a circle add up to? That's what your exterior angles add up to, 360. It doesn't matter whether it's a 100-sided figure or a triangle. The exterior angles, and here's what an exterior angle looks like. So if I go up here and I extend a side and create an angle on the outside of the polygon, so if I extend this side right here, this right here is an external angle. And I can turn this like a pinwheel and keep creating all the external sides. So I'm going to extend this side, just one side, not both of them, and I get an external angle there. And then I'm going to turn it. I'm going to extend just one side of my line, bless you, and I create this external angle. I could do it by extending the other side of the line, and then I'll just turn it in the other direction. And then the last side, I'm going to extend this line here, and there's my angle. So if I've got a four-sided figure, I have 4 exterior angles. And then all 4 of these angles right here will add up to 360 degrees. It's not because it's a quadrilateral. The same will happen here, 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 and here. The angles just get smaller and smaller and smaller. Okay? Also, tell me if that's an external angle and this is an internal angle right there, what do they add up to? 100% of the time. 180. So an external angle and an interior angle will add up to 180 degrees. So what you might want to do is kind of off here to the side. Maybe we'll draw it out here. Interior angle plus exterior angle equals 180 degrees because they create this straight angle, right? Or linear pair. So let's fill in this part. If a polygon is, and again it must be convex, this does not work with concave polygons, neither one of these do, then the sum of the measures of the exterior angles, one at each vertex, is 360 degrees. And so you're going to forget that. And the key to this chapter, or the key to this section, is knowing your external angles and knowing that they add up to 360 degrees. It's the way to easily find any answer. Yes?
What was the interior plus exterior?
180. All right, so flip it to the back, and as you will see, the interior and exterior sum theories have been restated for you. So you might want to highlight those again, just so that we are quite clear about the formulas to use. I'm going to give you a couple of extra formulas. We're going to go through a few problems here. So let's look at number 1. This one says find the sum of the measures of the interior angles. The only time that you're ever going to see me use the sum angle theorem for the interior angles is in this specific question. So in this question, over here to the side, we're going to use the sum is equal to 180 times n minus 2. Any other time I'm going to use my external angle. Any time I can use my external angle to find something, I will. And so you need to use your formulas. The more times you write it down, the more likely you are to remember it. So you're going to write this down first, then you're going to input into the formula. So I've got S equals 180 times, they've given you, it's a tengon. If I were writing the test, I would have written a decagon so that I could determine if you knew how many sides there was, right? So I'll write it as a decagon so that you have to go, oh, that's 10 sides. So you have to have that knowledge. So then we're going to replace n with 10 minus 2. I will assume that you're using a calculator, but you are using your calculator as a tool. You are not writing nothing on your paper. So I would still expect, whether I'm using a calculator or not, to see that 10 minus 2 is 8. And then you're going to multiply the 8 through, which we can actually do without a calculator. 8 times 0 is 0. 8 times 8 is 64. Carry the 6. 8 times 1 is 8. Plus 6 is 4. So the sum of the interior angles of a decagon is 1,440 degrees. Regular or not, doesn't matter, 1,440 degrees. Then you'll see that the rest of these keep using the word regular. Regular polygon, regular polygon, regular polygon. Because a regular polygon, all the angles are equal. So look at number 4. Find the measure of an exterior angle. So I need an exterior angle. Oh, I'm sorry, they gave me the measure of the exterior angle is given. Find the number of sides. So I want the number of sides. The formula for the number of sides would be 360 degrees divided by your external angle. If all external angles in a regular polygon are the same, and I know that all external angles add up to 360 degrees, can't I just take 360 and divide it by my 30 degrees? So n is equal to 360 degrees divided by 30 degrees. My zeros cancel, and my degrees cancel also, by the way. And then 3 cancels into 36 12 times. So isn't my number of sides equal to 12 sides? By the way, I can reverse this also. If they give me my number of sides, which they're going to do right here. So the number of sides of a regular polygon is given. Find the measures of an interior angle and an exterior angle. Go for the exterior angle first. It's the easiest one to find. I would not use this sum angle theorem right here at all. So this time, I'm going to switch these two around. Couldn't I take my external angle? Wouldn't it be equal to 360 degrees divided by n, the number of sides? It's going to equal the same thing. So what I would do is find your external angle first. So number 1, find your external angle first. So external angle equals 360 degrees divided by number of sides is 18. How many times does 18 go into 36? 2 times, and so it goes into 0 times. So 18 goes into 360 20 times. So isn't that 20 degrees? How are you going to find your interior angle? Yeah, so your interior angle is very easy to find now. 180 degrees minus the 20 degrees you just found, which is 160 degrees. So go for that external angle first. Your book will tell you to use the sum angle theorem. Ignore it, that's ridiculous. Use this, it's much easier. Then, the last problem, number 10. The measure of the interior angles of a regular polygon. They're going to try to suck you into, don't you dare pack up. They're going to try to suck you into using that sum angle theorem. If they give you the interior angle, can't I find the exterior angle first? How do I find it? 180 minus the 157.5 degrees, which is 22.5 degrees, am I right? So there's my exterior angle. What can I do with that to find the number of sides? Use that 360 formula, right? So 360 degrees divided by the 22.5 that I just got. And I would expect you to do that on your calculator. That gives you 16 sides. That is easy. You can use the sum angle theorem, but it's a pain in the butt. This is much easier. All right, now, your homework,